Hey physics fans, today we're talking about text problem 10-70 in your OpenStax textbook. Now problem 10-70 asks you to solve for the moment of inertia of a thin rod about some axis that's not going through the center of mass of the rod. So we know that this is a moment of inertia problem. Our task is to figure out an algebraic expression for the moment of inertia. Our physics, we need to know the equation for calculating the moment of inertia through direct integration, because that's how it asks us to solve it in the problem. Additionally, it asks us to check that moment of inertia using the parallel axis theorem, which means we need the parallel axis theorem and the equation for the inertia about the center of mass for a thin rod. The last thing we'll need is the linear mass density, which is the mass per unit length of our rod, to do our direct integration. Now in our draw step, we have our thin rod, which I've shown here, and I drew a dashed line for the axis through the center of mass, which we'll need for the parallel axis theorem. Now the axis we're rotating about is 1/3 of the way up the length of the rod, leaving 2/3 of the rod on the other side of our axis of rotation. So we're going to set our reference point for our position vector at the axis of rotation and integrate across our rod. We're given the mass of the rod and the length of the rod, and in order for this to work, we have to assume that there's a uniform mass density. In our solve step, the moment of inertia is the integral of our position vector squared times some mass element. Now, that mass element is equal to the linear mass density times some position element as given by the relationship in our linear mass density. Once we substitute that relationship into our integral, we can set the limits of integration starting at our axis of rotation, going from negative L over 3 to twice the length over 3. Taking the integral in terms of our length element dr gives us the position vector cubed divided by 3 times our mass density, which is the mass divided by the unit length, and we have to evaluate across our limits of integration. Substituting our limits of integration into our expression gives us the following expression for our moment of inertia. And evaluating that expression gives us 1/9 times the mass times the length squared. Let's check it. Using the parallel axis theorem, the first thing that we have to find out is the distance between the axis through our center of mass and our parallel axis, which is our axis of rotation. And using simple geometry, we note that this is the length divided by 6. So we can then write the parallel axis theorem as the inertia of our system is the inertia through the center of mass, which for our rod is 1/12 times the mass times the length of our rod squared, plus the mass times the distance between our parallel axis and the axis through the center of mass, which as we said is the length divided by 6 squared. And evaluating this expression gives us 1/9 times the mass times our length squared, which checks out with our method of direct integration. Thanks, physics fans, and we'll see you next time.